Hi, I'm Chau, working independently on the Thesis, and I'll be talking about my project to use light emitting diodes to provide white illumination and free space optical network. In this presentation, I will cover my project description, some background information and my motivation for this project, the general system design, my current progress and future work, and my results. The main goal of this project is to integrate networking and lighting together. And there are many requirements which I will discuss in the future slides. Now, one of the reasons for using LEDs is that they are likely to replace traditional lighting in the future due to their greater efficiency, as shown in this plot, and their longer lifespan. But why use them for networking? Well, for one, because they can be used. LEDs can be switched on and off quickly without damage, and therefore they can be used to modulate light. In turn, they can provide networking wherever lighting exists, even in places where Wi-Fi can't, for example, due to radio frequency interference. Imagine what can be done with internet access everywhere. There is also the potential for beating Wi-Fi speeds in the future, due to the larger available bandwidth and the minimal interference between different beams in different places. As an extra bonus, you get privacy due to the fact that light doesn't easily penetrate most walls. Now, I'm not the first to do this. For example, there's a patent on an illuminator that uses ultraviolet light for communications. There's a work of the Visible Light Communications Consortium. And there's this optical transmitter-receiver pair, shown here, that's done by students last year. This system can achieve speeds comparable to that of traditional dial networking at distances up to 3 meters apart. It uses a narrow beam for better signal quality, but that narrow beam makes it harder to align, and concentrated light is not necessarily great for general illumination, since you want larger coverage. This system uses serial ports for the interface and uses 2 pairs of 9-volt batteries for its power supply. I thought I could do a few things to improve this project. Among them are megabits per second speeds, a standard Ethernet interface, much brighter lights, a wider beam for more light coverage and easier alignment, and the ability to use conveniently available power. There are also some additional features, such as small size. Shown here is the block diagram for the system. There's an access point to the left and the computer adapter to the right. These two are similar for the most part, and I will point out the differences where they occur. In this block diagram, you see the access point side of the system. One of the main differences is that this side has 3 LED channels, green, red, and blue, unlike the computer side, which has 2. Conversely, the computer side receives on 3 channels, while the access point side receives on 2. On both devices, an Ethernet interface, shown as a top left block, connects the device and hence the optical network to an existing network or computer. The processing unit shown at the center top configures the other parts of the system and passes information between the connected parts. On the left, you'll see the transmitters for 3 optical channels. Each channel has an encoder which helps detect the integrity of the data by making the signal easier to decode. The LED driver and LEDs, which convert the electrical signal into optical signals, and frosted lenses, which diffuse the light for eye safety and shape the beam. Using 3 channels of colored light has advantages over using just 1 channel of white light. Among them are that 3 channels can provide greater throughput than just 1 channel, and the lack of fluorescence and using colored LEDs means shorter fall times. This is because white LEDs actually produce blue light, which becomes white when it hits fluorescent material and makes it glow as a result. So the fluorescent material is used dims slowly, and that leads to longer fall times, longer periods, and slower speeds. The main disadvantage of using 3 channels, though, is the increased complexity. You might notice that each channel has a different number of LEDs. This is to help balance the intensities of each color, since different color LEDs produce different amounts of light. As mentioned before, the computer adapter only transmits on 2 channels, and this is due to power constraints. For convenience, the computer adapter draws power from USB ports, which provides less power than is available to the access point. On the receiving side to the right, the optical signal is converted back into an electrical signal, amplified, filtered, and decoded. Going back to the transmitter, driving the LEDs was the most difficult challenge tackled in this project. While the LEDs are on, they need to be driven with a carefully regulated current. This is because, for the most part, the current controls the brightness. Controlling the voltage across the LEDs alone is insufficient, since the current voltage relationship varies between different or even the same LEDs due to manufacturing variability, temperature, and age. Also, the LEDs may become damaged if the current is too high, and is unpredictable if the current is too low. The driver also needs to switch a large amount of current to drive these high-power LEDs, and needs to do so quickly in order to enable high-speed communications. At first, I tried to find a commercial off-the-shelf solution for the LED driver. However, every driver encountered fell into one of the 2 categories. The first being commercial off-the-shelf constant current drivers and LED drivers, which were able to provide enough regulated current, but were not able to switch that current on and off fast enough. The other group of drivers encountered were that for fiber optic systems. Since they were created specifically with high-speed communications in mind, they can switch fast enough, but unfortunately they were not able to provide enough current for illumination. Since no existing solution was available, I had to design a custom LED driver. Shown here is a schematic. The top part does switching, and the bottom part does the current regulation. A MOSFET driver, this box, individually controls the 2 NMOS transistors that form an inverter that drives the LED. I could have replaced this with a simple CMOS inverter, but this design eliminates shoot-through current, which is essentially a momentary short circuit between the positive and negative rails of the circuit. In series with the cathode of the LED is the constant current portion of the circuit. And mainly it's an NMOS transistor with a resistor and an op-amp for feedback. And voltage measured across the resistor is used as negative feedback in the op-amp to control the NMOS transistor to keep the current through the LED at the desired value. However, when the LED is off, the lack of current through the resistor will cause the op-amp to turn the NMOS transistor all the way on, which may result in a huge surge through the LED when the LED turns back on. The other components there exist to reduce the effects of the LED being off on this transistor. A SPICE simulation of that circuit shows that when the LED should be off, almost no current flows through the LEDs. And when the LED should be on, approximately 350 milliamps flows through the LEDs. These are the desired values. The simulation indicates that there is, however, a momentary spike in the current on the off to on transition of the LEDs. But the peak of the spike remains below 700 milliamps, which is safe for the LEDs. This driver is able